Hey everyone, I wanted to do a quick video on ionic bonding and naming. This tends to be a difficult topic for most people, but we'll break it down so that it's really not at the end of the day. I'm working off of exercise 8.3b, the worksheet I handed out to you, and I'm just going to kind of start with a couple prime examples to kind of lead you through this. When it comes to ionic bonding, the main two, actually maybe even three questions you need to ask yourself is it regular ionic bonding? So you have your cation and your anion. Is it metallic ionic bonding, which in case we're using a metal, and we have to indicate that metal's charge using Roman numerals in parentheses. And then we also have another form of ionic bonding called polyatomic, as opposed to the monatomic regular ionic bonding. And the polyatomic ionic bonding is literally a polyatomic ion, something like PO4 3-, something like this, which you'll need your polyatomic common ion sheet in order to do. Let's go ahead and start off with regular ionic bonding first. In regular ionic bonding or monatomic ionic bonding, we have to take, we go ahead and take the cation and we bond that with the anion. So for example, something like potassium, K, we go ahead and check the charge, so that's K plus for its ion, potassium ion. And then we bond that with something like, I don't know, bromine or bromide, since it's an ion. And since bromine or bromide has a negative charge and potassium has a positive charge, we're looking for our overall charge when bonded together to be 0, or our net charge to be 0. So in this case, I can put potassium bromide together just like this. To check myself to make sure that I'm actually doing this correctly, I look at my 1-to-1 ratio. I have 1 potassium at a positive 1 charge. So I have a total charge on that as +1. I have 1 bromine at a -1 charge. My total charge on that is -1. That does give me a net charge of 0. This is what my answer that I'm writing down for it. I'm not including those charges. That's just a way to check myself to make sure I've put it together in its correct way. Something a little bit more complicated than that would be combining it with another monatomic ion. For example, let's say something like, we'll keep our potassium and we'll put it with oxygen. Well, when oxygen becomes an ion, it's going to be oxide, and it gains it has a -2 charge using your periodic table. Now I have to put these two together. I cannot put them in a 1-to-1 ratio. The reason why is because technically I have a -2 charge here. That means I need 2 of these potassiums in order to balance out and give me a net charge of 0. I'm going to check myself. 2 times +1 is +2. 1, it's implied even though it's not written, is times -2 is -2. And that gives me a net charge of 0. Something like that. So that's regular or monatomic ionic bonding. Now, we're going to go ahead and switch over to polyatomic ionic bonding before we jump into the metals. So polyatomic is when we have something like, I'm going to do number 1 on the 8.3. It says they want me to tell me the formula for sodium nitrate. All right. Well, sodium is Na. The sodium ion is Na+. Nitrate, I'm going to look at my polyatomic ion chart and realize that it is NO3 minus this entire ion. Well, this entire ion acts as 1. I don't have to think about my nitrogen charge. I don't have to think about my oxygen charge. I don't have to think about what proportions they are to each other. They act as 1. So therefore, I can go ahead and treat it as one entire polyatomic ion. And when I bond these together, I have still a 1-to-1 ratio here, Na, NO3. just like that. All right. So the NO3 is carrying a -1 charge. I have one of those. There's not a 1 right here. There's 3 oxygens, yes, and a lot of people will confuse this. I'm looking at the entire thing, technically. I'm looking at NO3. I only have one of those. I do not use my parentheses quite yet because I only have one. If I had more than one, I'll show you that in a second. So NO3 is a -1. I have a total of -1 charge. Na is a +1. My overall net charge is 0. So this is what I'd write down for my answer. That was the answer to number 1, sodium nitrate. Now I'm going to go on and do something a little bit more difficult, like number calcium nitrate. No, number 13. I'm looking for one that would give me something else. I'll just make one up just so you can see. Let's say that I'm still going to take sodium. And instead of bonding it to nitrate, I'm going to bond it to sulfate. Well, my sodium again is Na+. My sulfate, according to my polyatomic ion chart, is SO4 2-. Now, I cannot put these in a 1-to-1 ratio, obviously, because this is a +1, this is a -2. So therefore, I have to combine them. I would need 2 sodiums in order to have a net charge of 0. Na2SO4. I'm going to check myself. Technically, I have 1 sulfate ion at a -2. I have 2 sodium ions at a +1, therefore giving me a total of +2. That does equal 0. Na2SO4 sodium sulfate. Now, what if I needed more than 1 polyatomic ion? Or what if I had a polyatomic ion that came first as a cation? Well, NH4+ ammonium is one of our only polyatomic cations. I'm going to go ahead and combine that with oxygen, or oxide in this case. So I'm always going to write my cation first again. So it's NH4+, and I would need, this is not a 1-to-1 ratio, I would need 2 of these in order to balance that out. So here's what you do when you need more than 1 polyatomic ion. You put it in parentheses, and you say, hey, that whole ion there, I need 2 of them. Some people will do something like this. All of a sudden I have 42 hydrogens. That doesn't make sense. Some people do something like this. Nope, technically that doesn't work either. That's something that will be done later. Some people will distribute the 2. They'll say something like this. No, that is completely a different molecule. So therefore, we can't do that either. The only proper way to indicate multiple polyatomic ions is with parentheses. I would need 2 of these, oxygen there. So I have 2 NH4s, 2 ammoniums, 1 oxide, and I'm just going to check this. I have 2 times +1 is +2. 1 times -2 is -2. I have an overall net charge of 0. That is my answer for ammonium oxide. The same thing happens if you were to put that in the back. For example, let's say I'm going to do, keep looking for one of these that are not metallic on the worksheet, but I'm not finding it while I'm looking for it. Calcium nitrate, number 13, calcium nitrate. No, yes, perfect. Okay, calcium nitrate, number 13. My calcium is Ca. I know that it's a 2+ charge. Nitrate, according to my polyatomic ion chart, is NO3-, just like this, right? So, not a 1-to-1 ratio. I need technically 2 of these nitrates. Again, Ca parenthesis, NO3 parenthesis 2. I'm going to double check that I've actually gotten this right. 2 times -1 is a total of a -2. 1 times +2 is a +2. That does give me an overall charge of 0. I would write this as my answer. I don't leave any of that stuff there, any of the charges. That's just a way of checking myself. So CaNO3 is your answer, number 13. Now, for the last part, we're going to go ahead and move on to metallic ionic bonding. This is when we have a metal. I'm looking at number 8. Never mind. Number 8 is a polyatomic ion. And I'm looking at number 14. Zinc 2 fluoride. Zinc I know is Zn. That right there, the number inside the Roman numerals inside the parentheses tell me my charge, not my number of ions. It tells me my charge of my ion. That is a +2 or 2+. All right. That, because this is a transition metal, we had that all the transition metals, most of them, have a variety or a large amount of different ionizations. Then technically, this one's telling us the +2. Now I know fluoride is a -1. This is not a 1-to-1 ratio. I would technically need 2 of those. So ZnF2, zinc 2 fluoride. Again, the 2 indicates the charge of the zinc, not how many atoms of zinc I have. All right, that was your answer to number 14. Now I'm going to do another example, manganese chloride. Manganese 3 chloride. Manganese Mn, that right there, inside the number inside my Roman numerals inside the parentheses is a 3+. Chloride is a Cl-. I would technically need 3 of these. 3 times -1 is a total of -3. 1 times a +3 is a +3. That gives me 0. So MnCl-. That's the answer to number 16. All right, now let's combine what we've learned so far into one of the harder examples, something like number 8. Lead 2 chromate. All right, lead, Pb, the 2 +2. Chromate is a polyatomic ion, and it is Cr O4 2-. That's my chromate, that's my lead. It's in a 1-to-1 technically because those pair each other, they match each other, or they cancel each other out, I should say, and give me a net charge of 0. Pb Cro4. All right, and that would be how I do that. Just quickly, one more example of that when I'm bonding. And this is taking the name and putting it into a formula. We'll go reverse in just a little bit on another video. Cobalt 3 sulfate. Cobalt 3 sulfate. And this is number 33 on your worksheet. Cobalt, CO. That 3 tells us it's a +3. Sulfate is SO4 2-, like so. Now, 3 and 2 do not cancel each other out. +3 and -2 do not give me a net charge of 0. So I have to go with my least common multiple of these two, which would be 6. Now, there's a little faster way to do this, but I'll show you that in a second. 2 would go, so I need technically a -6 or -6 and a +6 ultimately, right? So CO, what times +3 equals +6? 2. SO4, I'm going to put parentheses around it because I'm going to need multiples. What times -2 equals -6? That would be a 3. CO2, parenthesis, SO4, parenthesis, 3. Cobalt 3 sulfate. Now there's a faster way to do these types that a lot of people will tell you. And it's not to worry about your least common multiple or anything like that, but instead just to switch. Notice it'd be CO2, SO4, 3. I literally just put my charges, I switch my charges to each individual or each opposite ion there. Same thing, all right? And when I check myself, 3 times -2 is -6, 2 times +3 is +6. That does give me an overall net charge of 0. That's just a faster way to do it. All right, I hope that this has helped you on 8.3b without me having to be there. I've explained the majority of ionic bonding in terms of taking names and turning them into formulas. The next video will be turning formulas into names.